Electrostatics. Here we're seeking to know the value of the electric field, and we don't know all of the charges involved in the situation, but we have this large metal object that is charged, and it has carrying a negative charge. Next to it, we're going to hold a small aluminum sphere that has a given amount of charge, minus 1.55 times 10 to the minus 8 coulombs, and it's attached to a massless string, and this string has a length of 28 centimeters. So that's going to be our situation, and I'll make a little drawing here to deal with the top end of the string being above the right edge of the object, and then the repelling. This won't be to scale, but give you kind of a sense of what's involved here. So we've got this oval object. The anchor point for the string is above the right edge. So if I draw a vertical line down, it comes like that, and I'll make that go in just a little bit. And this is not to scale, but right across here we've got the separation of this metal sphere from this metal oval object of 0.6 centimeters and 28 centimeters for our string. Well, why is this metal object not hanging straight down? Well, the oval object carries negative charge. There's negative charge on the sphere. They repel each other, and we want to make use of the geometry here, the numbers, to somehow be able to calculate the electric force. Our basic scheme towards the end of what the work done in this page would be that the electric force that this charge experiences divided by the value of this charge gives us the value of the electric field at this point. So that's where we're headed in all of this. So on the sphere, there are three forces that exist. I'm going to draw it over here. So the sphere, there's tension in this string. There's the electrical force that's repelling, and then there's the weight of the sphere. Those three forces are in equilibrium, and we're going to work this out with x and y components. This string has an angle theta away from the vertical, and we'll find the value of that in just a minute. But if I want to know the x component of the tension, which trig function should be used? Where everything would be in symbols here. So unknown tension of the string. We've got a right triangle. How do I obtain the value of t sub x? Theta is up at the top of this triangle. Which trig function? You should be saying sine of theta would produce that. So in the horizontal direction in x, we've got Fe to the right and t sine theta to the left. Those have a net force of 0 because we're in equilibrium. In the y direction, what is the y component calculation for the tension? Well, we're adjacent to theta, so it is the cosine function that provides that. So in the upward direction, t cosine theta, downward mg, so I put a minus sign on that. I'm working this with positive being upward and positive being to the right for the x calculation. So there's some start to this. We want to get Fe. We want to get a value for Fe. We don't know the tension. So let's see if there's some way that we can get rid of the tension. Well, there is. If I'd rewrite the x as t sine theta equals Fe, I can add t sine theta to both sides, and I'm going to put t sine theta on the left. Doesn't matter which side of the equality this appears on. So add t sine theta to both sides, and then I'm choosing to start with t sine theta and then equals Fe. For the vertical direction, I'm going to add mg to both sides. So in doing that, we'd have T cosine theta equals mg. And now I'm going to divide these two equations. This is allowed. I have T sine theta divided by T cosine theta. That's going to cancel the T's, and sine theta over cosine theta produces tangent of theta. On the right side, Fe divided by mg just produces that, Fe over mg. So I'm dividing both sides. The left side, T sine theta divided by T cosine theta. The T's cancel off. Sine theta over cosine theta is reduced to tangent of theta. So we're to that far. Now multiply both sides by mg. We get mg tangent theta equals Fe. We're really close to finishing this. We know the mass. We'll have to convert that to kilograms. We know the acceleration due to gravity. Well, let's do a little side calculation here and find the value of theta. In this right triangle, in terms of distances, we don't know this vertical side, but we do know the base is 0.6 centimeters over here, and we have 28 centimeters for the length of the string. So which trig function is connected with opposite side and hypotenuse? And you should be saying sine of theta. So over here I'll do the work. Sine of theta is equal to the opposite side divided by the hypotenuse. So we have those numbers, and we can do that division, and we find that sine of theta has a value of 0.02143. Now take inverse sine of both sides. Inverse sine of sine of theta equals inverse sine. I have to take inverse sine of both sides, 0.02143. In this part, the inverse sine of sine of theta, these two functions are inverse functions of each other, and we just get the argument theta. Inverse sine of this you do on your calculator. Make sure you're in degree mode, and when you do that you'll get 1.228 degrees. So we found the value of the theta. We need that so we can get the value for f sub b. So let's go ahead and calculate f sub b. F sub b is 45 times 10 to the minus 3 kilograms. We're changing grams into kilograms. We've got 9.81 meters per second squared for the acceleration due to gravity. And now tangent of the 1.228 degrees. So use your calculator, multiply that through, and I came up with 0.00946 newtons. 0.00946 newtons. And now we come to the place where we calculate the electric field. The electric field is Fe over Q. We know the value of Fe. Just have recently calculated it. 946 newtons. 946 newtons. Q was given in the wording of the problem. Q is 1.55 times 10 to the minus 8 coulombs, and the fact that it's a minus sign does not affect this result. We'll talk about the direction of the electric field in just a minute, but let's just do the magnitude of the electric field. So 1.55 times 10 to the minus 8 coulombs, and doing that on your calculator, hopefully you get 6.1 times 10 to the 5th newtons per coulomb. Newtons per coulomb. So we found the value of the electric field by using condition of equilibrium in x and y equations to cancel off the tension unknown, finding the value of the electric field, finding the value of the electric force on the charge, and dividing by Q. So we have here a situation where this negative charge is repelled off to the right. The force is off to the right. The electric field does have a direction, and that direction is the direction that a positive charge would experience force. And if I would put a positive charge here, it would be attracted off towards that oval object. So the direction of the electric field is to the left. The direction is off to the left at the point where this test charge is located, where the sphere on a string. So an example of electrostatics, coming up with the value of the electric field through working out the value of the electric force and given the value of the charge. The direction of the electric field is the direction a positive charge would move. We have a negative charge here moving to the right. A positive charge would move to the left if it was free to move. So ask other students questions about this. Ask your instructor. Keep practicing.